So something more about electric field. The electric field line and the force experienced by positive charge have the same direction. While if there is a negative charge, the force is the reverse direction of the electric field. So in the first picture, a positive charge plus Q means a positive charge and minus Q means negative charge. So as you can see, the force experienced by a positive charge is the same direction as the electric field strength. And there is a little bit special case, which is the plate capacitance. Basically, it have two plates and they are connected to the battery. So one of the plates will have positive charge and another will be negative charge. So as electric field lines goes out from positive charge and goes into negative charge, the electric field strength between these two plates should be from the top to the bottom, as is shown. So for a negative charge, the force experienced by it will be to the top, the reverse direction of the electric field strength. Another thing that is really important is the superposition of electric field. So now suppose I have a positive Q charge and a negative Q prime charge, and we are going to study the electric field at P. So to solve this problem, we are going to use the addition of vectors. We will analyze the effect of positive Q and negative Q prime to the electric field at point P separately. So first, let's talk about positive Q. As we know that the electric field produced by a positive charge is away from it. So first, let's draw a line connecting the P and positive Q, and then a vector E1. And the same will be done on the minus Q prime charge. So we'll again connect the charge and the P together, and the electric field this time will be pointed into the charge because it is negative. So now we have already drew the effect separately. So what will be the overall electric field there? So because electric field is a vector, we are going to use the addition of vector and we'll get another vector E. So that is the overall electric field at point P. And sometimes in real tests we need to use some trigonometry methods to solve for the exact magnitude of E. And next we are going to study the electric potential energy. So we define the electric potential energy of a charged object that is infinitely far away from a Q is 0, as is shown in point A, which is infinitely away from Q. So therefore, the electric potential energy at point B, which is a distance d from the charge, is equal to the work done by the object when moving from point A, which is infinitely far away, to B. So here, the work done by the object may be kind of difficult to understand, so you might just remember it as negative work done on the object. So work done by the object is negative work done on the object. So let's assume that the big Q and small q are all positively charged. So when we move the small q to the big Q, there's a repel between each other. So the force experienced by small q is actually away from big Q, while the displacement of Q is pointed to the big Q. So the direction of displacement and the force is opposite. Therefore, the work done by the force or on the object is negative. Let me repeat. The work done on the object and by the force is negative. So the force is like a hindrance to the movement. So as we see in the definition, the potential energy is the work done by the object, which is the negative, the work done on the object. So the potential energy when we move Q from point A to point B is actually positive. So the potential energy at point B is positive when big Q and small q are also positive. So it's the same idea that you are climbing a hill. The force you feel is always away from the top of the hill. So the big Q here is like the peak of the hill, and small q is a climber. So he's facing great difficulties. The force is pointed opposite to his direction to get to the big Q. So the potential energy of it is actually increasing as it goes nearer to the top. So next, let's go through some numerical relationships of electric potential energy. So again, the electric potential energy at point B is equal to the work done by the object when moving it from point A, which is infinitely far away, to B, which have a distance d from the charge. So let's calculate the work here. The work is equal to the force times displacement. So we use an integral to calculate the force times displacement when we move the object from A to B, which is the integral from A to B, F times dx. So as the force is equal to k big Q small q over r squared, and the distance of A and B is respectively infinite and d. We could transform this equation to the integral from infinite to a distance d, k big Q small q over r squared, dr. And the result of this will be minus k big Q small q over d. Well, because we are calculating the work done on the object, and the electric potential energy is the work done by the object. So the potential energy is equal to minus k big Q small q over d, which is k big Q small q over d. So what if we want to calculate the change in potential energy when we move a charge Q from C to D? C and D are all of a certain distance from the Q. So first, let's use a relative difficult method to solve this problem. The change in energy is equal to the work done by the Q and minus work done on the Q. So the change in energy is equal to minus the integral from C to D, F times dx, which finally equals to k big Q small q over d2 minus k big Q small q over d1. Some of you might observe that k big Q small q over d2 is actually the potential energy at point D, and k big Q small q over d1 is the potential energy at point C. So the change in potential energy if we move a charge from C to D is actually the potential energy of D minus the potential energy of C. So the electric potential, it is defined as the electric potential energy over small q, which is the charge of the moving object, and it is equal to k big Q over r. Since potential energy is equal to k big Q small q over r, and the symbol of it is phi. The unit is volt, which is equal to joule per coulomb. And the potential also only have magnitude, and it is a scalar. So is the potential energy. And the relationship between the electric potential and electric potential energy is similar to the relationship between the force and electric field, like the Coulomb's law and the electric field. As we mentioned last time, Now the electric potential only concerns a single charge instead of two charges, as is shown in the equation that the potential is equal to K big Q over R. Also, there is an important relationship between the electric potential and electric field strength. The potential difference between A and B, which is phi B minus phi A, is equal to the integral of E times dl, which is the distance from A to B. And here's all the relationship between electric potential energy, electric potential, force, and electric field strength. The big U, which is the difference in potential energy, is equal to the integral of E times dl from A to B. And the change in energy is equal to the integral of F times dl. The change in potential is the change in energy over Q, and electric field is equal to F, the force, over Q. You might find some relationship between these four equations, and actually the last two provide some explanations to the first and second one.